Thank you very much, and thanks to the organizers, well, to Herbert, Christoph, and everyone else involved in the organization for the opportunity to talk. So I will report on, well, this is a program which has been going on for several years, and I will mostly focus on joint work with Eric Sawyer and Chun Jensen, but you will see there are some other pieces which are also joint work with Michael Lacey and Brett Wick. So the main object of interest is we want to characterize the pairs of weights, meaning locally finite Borel measures, for which you have this norm inequality. Okay? We only do p equals 2 because basically it's the only known case. Well, I mean, there's a little bit known in general p, but basically nothing. No? So I have recorded here, and I will put it up later, the norm inequality here at the top of the board. And the best constant, we call it n for norm. Okay? So there are several ways to try to characterize this kind of norm inequalities. If you look at one single weight, there's a very well-known characterization of Mack-Haupt that basically it has the advantage of being a necessary and sufficient condition and also of being very easy to test or reasonably easy looking to test. As soon as you go into the two-weight world, well, there's been a lot of work in trying to get Mack-Haupt A2 type characterizations. The obvious condition for two weights for Mack-Haupt type is necessary but not sufficient. And then there's a whole industry of, research trying to strengthen slightly those Mack-Haupt type conditions to see if you can get a necessary and sufficient conditions. And there's the so-called bump conjecture. Actually, the two-bump conjecture first, which was solved by basically, Sasha Volberg and other collaborators. And then there's still the one-bump conjecture, so on. So this is a different avenue that we are dealing with. Okay. So the advantage, the difficulty with the two-weight Mack-Haupt type conditions is that so far they have produced very sharp sufficient conditions for boundedness, but they are not necessary and sufficient. The advantage is it's easier to check, and it's also independent of the operator. So another approach is the approach we are taking here. It's T1 type characterizations. The advantage is that it's if and only if conditions, if you succeed, of course, improving them. The difficulty is that the testing conditions involve the operator, and then it's harder to check. But if your life really depends on knowing whether this bound is true, and you cannot verify, sort of the Mack-Haupt type conditions, then you may want to go back to this. No? And also, I think it provides a nice understanding of how certain operators work. No? So this kind of T1 type characterizations, if you go back to, let's say, 2 years ago or 3 years ago, this was the state of the art by then, okay, which were known basically for positive operators, or fractional integrals, Poisson integral, maximal function, for the Hardy operator, and for discrete singular integrals, Nassarov-Trial-Volberg have a paper in that respect. No? And continuous singular integrals are considerably harder, which is the object of what we are going to do now. So the conjecture is most important when T is the Hilbert transform. This is known now. I will report on that later. Berling transform or Riesz transforms, it's not known. And this type of question occurs in different instances. For example, the Saracen conjecture on composition of Henkel operators. Well, and this sort of other contexts in which I am by far not an expert. But anyway. So there is, here I was explaining a little bit more how it's known for Poisson integrals, fractional integral operators, and the dyadic case, well-localized or band operators by NTV. Now, if you look at the L2 case for Hilbert, there is a characterization by Kotler and Sadowski, but it's not real variable. We're trying to get real variable. I will explain in a moment what kind of characterization we want. So the first milestone in this area, in this approach, was given by Nassarov-Trial-Volberg. So I will explain a few conditions, and then the question is, do these conditions characterize the norm inequality? So the first condition is similar to the classical A2. So if you take two weights, omega and sigma, and you put the average of the two weights, if you take the soup over all intervals, that's the classical A2 condition. Here we do fattened A2. So we fatten with some Poisson tails. No? Now we are in one variable. So the fattening is this one. Okay? And this is bigger, so this is a stronger condition. This condition is known to be necessary for the two-weight norm inequality to hold. Okay? Then Nazarov-Trail-Goldberg introduced the so-called pivotal condition, which basically says, well, for any interval, you decompose the interval into an arbitrary decomposition of intervals IR. And you have this kind of control, that there exists a constant P so that this thing holds, and the corresponding dual. I forgot to say one big advantage, let me go back for a moment. One big advantage of this formulation is that it's very easy to dualize. The dual is simply you change sigma and omega. You interchange them. Okay? So you have the pivotal condition and the corresponding dual, which is changing sigma and omega. Okay? And then there are obvious necessary conditions, which is the so-called testing conditions, or T of 1 type conditions, which is basically saying, well, you want this norm inequality, here I'm writing it for H, the Hilbert transform, to hold for some constant, which I'm calling here H, for all functions. Well, instead of that, the T1 type approach says it's enough to test over a reduced class of functions, namely, in this case, characteristic functions of intervals. And moreover, you need only to test over the interval itself, I. Okay? So the best constant for this reduced class of functions, we call it H. The corresponding dual, we call it H star. Okay? And then their theorem, and also it's also a statement of their conjecture, is that assume you have pairs of weights which have no common point masses. This is a mild technical assumption. It's not, well, I mean, okay. And assume you satisfy the pivotal condition and the dual pivotal, which were these two conditions. Don't worry if you don't recall them, because they are soon going to be removed. I mean, this was important, a very important milestone, and actually it's now embedded in the proof, in the actual proof, but they're going to be removed as assumptions soon. Okay? So now the two-weight norm inequality for the Hilbert transform holds if and only if you have A2 testing and dual testing. And actually, you even have that the best constant, the n, is comparable to these three constants. Okay? So the big conjecture at the time was whether you could remove pivotal or whether they were necessary or not. No? So well, I don't know how much you can see, but I recorded here this is the norm inequality. This is the A2 with the Poisson, and the testing and the testing. These two things will appear later. Okay? So, and the question is whether the norm inequality holds if and only if you have this. Okay? And this will, as I said, first you do Hilbert, and then you try to do the rest. Right now, Hilbert is done. The rest, we don't know, basically. I mean, I will. Okay. So, thanks. So, the Nazarov-Trail-Goldberg further stated in their paper that the pivotal conditions might be necessary, but, well, it was not known at the time. So, Michael, Eric, and I proved that it's not necessary. Okay? I will explain a little bit in a picture one possible example, okay, for this. However, let me remark also that if the measures involved are doubling, pivotal is true. Okay? So that already covers a very nice class of measures. So the enemy is the non-doubling measures, which these non-doubling measures will make you lose control in stopping cubes. I'll emphasize in a moment later how. Okay? So let me give a quick picture of one possible example right here to prove that which also highlights another idea, to prove that the example used to prove that the pivotal is not necessary, the pivotal conditions. Okay. So you take the 1/3 Cantor set, okay, and so on, okay, and the corresponding measure, the standard measure, probability measure here, is the weight omega. Okay. And the measure sigma is going to be a sum of delta masses. So the first attempt, which does not work, but it's still useful to remark, is you put delta masses in the, in the centers of the gaps. Okay? And you put a corresponding mass so that basically A2 is satisfied. That's easy in the sense that you test this guy against the mass of these two. This gives you the best constant so that the A2 tested over this triple interval is basically 1. And then it's easy to check that the rest holds because then you have a geometric, you have a geometric series that adds up, so that's enough, okay? So you try this. This satisfies A2. So let me put here sigma, sigma, sigma. This satisfies A2. It satisfies the testing, but it does not satisfy the dual testing. And it's known that, A2 testing and dual testing are all necessary. So then it cannot satisfy the norm inequality, okay? It was already known before that there were examples. Basically, the Saracen conjecture at the beginning could be formulated in terms of, is A2 necessary? This was disproved by Nazarov. Then you could say, well, maybe A2 on one of the testings. This was disproved by Nikolsky and Trial, basically. Well, they had an example in which the dual testing was not satisfied. That's what I mean, because dual testing is not necessary. So this is another example of that. So we were not the first to do that. However, this example is useful, you will see in a moment, to disprove that pivotal is necessary. So now, instead of this one, you just move the sigmas a little bit. A little bit means, so if you consider h of omega, okay, and this is the corresponding generation of the Cantor set, h of omega in the gap is going to look like this, more or less. Well, so you put the sigma in the 0. We have an estimate which shows that, here it's of course in the center, but here it's going to be tilted, okay? We have an estimate that shows that the 0 is not too far away from the center. We can do that quantitatively. If you do this, the same masses of sigmas, etc., this satisfies the weighted norm inequality, but it does not satisfy the pivotal condition if you choose the parameters appropriately. Okay? So this is supposed to tell you a bunch of things, but one of them is, as I told you before, you're just moving it a little bit. So this problem is extremely unstable. So forget about numerical experiments. And it's, well, it shows, in a sense, or it hints at how delicate this kind of thing is. No? But anyway, this is an example that works. I should also explain that, here there is a little bit of a catch-22 approach, problem, no? Because, okay, I said, this doesn't satisfy pivotal, but it satisfies the two-way norm inequality. Okay, how do you know it satisfies the two-way norm inequality? You need a sufficient theorem. At the time, the only one was the one by Nazarov-Trail-Wahlberg. So what we did was, at the time, we introduced something called energy condition, which produced a range of conditions. The weakest one of those was pivotal, and each one of those was sufficient. So for any fixed parameter of that range of parameters, we could build this so that it didn't satisfy the previous ones, but satisfied the one in the range you wanted. So none of those conditions, which you can think of as generalizations of pivotal, were actually necessary, but at the time nothing more was known. No? So the next, big step was, well, here is the recollection of what the Hilbert transform is, and now, instead of testing over intervals, let's for a moment test over L infinity functions. Okay, so the best constant, we call it H infinity, and the corresponding dual. So the first main theorem, well, or the second, depending on how you look at it, but anyway, main theorem of this collaboration is that you have the weighted, the two-way norm inequality is comparable to A2 and this testing over L infinity functions. So this was the first if and only if condition. It's not, there was no, no side condition. It's easy to see that testing over L infinity functions is the same as testing over characteristic functions of measurable sets. That's very easy. That's a half a page proof. And in this theorem, if you look at the literature now, In this theorem, we made what's now called the global to local reduction. Okay, that's a standard. I mean, that's the terminology in the papers, in the latest papers. So as a corollary of this theorem, you have something that already appeared in the solution of the A2 conjecture, which is that the strong norm inequality is equivalent to the two weak inequalities, the weak and the corresponding dual. Okay, and well, I mean, it's nice. Anyway, the proof of this, assuming the theorem, the proof of this of the corollary is very short. Basically, you assume that you have the weak inequality with constant W. You dualize. This is essentially the restricted strong type inequality, and this is if and only if you have this inequality, because the Lorentz space L2-1 allows you to add up, and then you immediately get one of the testing for L infinity bounded by the weak testing. Then you have the corresponding dual and the necessity of A2, and it works. Okay? Good. So we are right now at the point where we have to test over characteristic functions of measurable sets, or finite unions of intervals, but arbitrarily. The conjecture, the NTV conjecture, was that it's enough to take intervals. So this step was finished by Michael Lacey on his own. That's what's now called the local term. So his theorem was that you can handle that. And the idea is a very clever recursive proof, which is somehow reminiscent of the approach that Michael and Christoph had for the proof of the Carlesson almost everywhere convergence, and stopping time which goes bottom up in a certain sense. So if you put together the two things, actually they are going to appear as parts 1 and 2, but as I said, part 2 is just Michael. You have the main theorem, you assume locally finite Borel positive measures, no point masses in common, you have the NTV conjecture. So the norm inequality is comparable to the 2 testing and the A2 in a quantitative way. Then Hitonen, a little bit later, removed the condition of no point masses in common. So the way he did it, if you think of A2 prevents the point masses in common to occur because you have sigma on an interval and omega on the same interval. So if you have a point mass, you blow up. Well, so he just considered the A2 condition with holes. So for example, you integrate sigma on a certain interval I, and the omega you do the Poisson tail, but outside I. And this is one of the A2, there's the corresponding dual. You run the whole proof. I'm not saying it's trivial, but it's the proof, the scheme was known. You have to prove a T1 theorem for the Poisson operator like Sawyer, but with holes like this, but it works. And then you get the NTV conjecture for general radon measures. Okay. Yep.
What does H mean?
H is, oh, you mean this side, not this side. Yeah, I should have said the way to understand this is that you have uniform estimates for all truncations. That's how you define the norm inequality. Sorry, thanks. So where are we? Yeah. Okay, so then you try, now we understand one dimension, you try to move up in dimensions and other operators. So the previous theorems are very one-dimensional, and I will emphasize different aspects of this, okay? But let's start with a very simple, a very simple instance in which you can see the one-dimensionality. So let's assume you have one weight for a moment. You take the Riesz, in Rn, well, actually it would be R2, but anyway. One of the Riesz component, the vectors of the Riesz transform. No? So let's say the second component. So with one weight, the boundedness of this single one already implies that the weight is an A2. This is, for example, in page 198 of the FAT book by well, anyway. So as soon as you do two weights, this is a very simple-minded example, but it already shows you that there's a little glitch. It's not too hard to see this one. No? So let's assume you have two weights supported on the x-axis in the plane, and the second Riesz transform automatically is the zero operator, simply because the kernel is zero. This is obvious. So then the boundedness of one single operator tells you nothing about the measures. So this tells you that you need something more, no? So, well, the theorem below, I mean, basically, is if you have a vector of fractional Calderon-Sigmund operators, which are sufficiently elliptic, this means, for example, the vector with transforms, or just the single Berling transform, or other ones, then the A2 conditions with tails are necessary. Without tails, this was known by, I mean, it was published before by Constance Liao and Sergei Trial, even for all P's. Okay? So, okay, so the A2, I mean, they are necessary, fine. This is the next thing is that, well, A2 here in higher dimensions has a certain glitch. So let me explain. There are two kinds of Poisson kernels that appear in higher dimensions. So we are considering a singular integral, sorry, we're considering fractional singular integrals. So the kernel has, I mean, singularity n minus alpha. Alpha equals 0 is in the singular integral case. And you get, on the one hand, the so-called standard Poisson integral, which is this one. Here, this is Lebesgue measure, I mean, the volume. So this is the side length of the cube, Q. And in the necessity proof, you naturally get the so-called reproducing Poisson integral, which is, well, the same things, but to a different power. And this guy is the one that's bigger than the classical fractional A2. So in the case of the Hilbert transform, these two guys coincide. In the general case, they don't. And then they have to talk to each other. Because when we say A2 is necessary, we use this one. When we want to get sufficiency estimates, meaning as soon as you want to say testing plus A2 is enough to get the boundedness, you need to use this guy. And as I said, they are not equal, so that creates a complication. Okay? So the next, well, this is, here I'm reminding what's the classical A2 and the one tailed A2 constants, as I said, with this type of Poisson kernel, the reproducing one. Okay. Again, we have the cube testing conditions. This is completely analogous to the one-dimensional case, I mean, the same story. We have the weak boundedness property. Don't worry too much about this because it's going to disappear in a moment. But in any case, it's analogous to the David-Journet T1 case, which basically says whenever you test in cubes, one cube inside another outside, which are basically neighbors, of more or less of the same size. So then you get a certain constant. No? This is not, I mean, as the name suggests, it's weak. For example, it's implied by the triple testing condition, or it's dual. It's very easy to see. So the point is, if you can test the testing condition, it shouldn't be too hard to also test this one. So, but as I said, this is going to disappear in a moment, so don't worry too much about it. There is a, okay, maybe I should skip for a moment these two slides, and I'll go back to them in a moment. So the theorem we get, Sawyerson and myself, is that, again, you have positive Borel measures without common point masses. You have the norm inequality with the best constant. Again, it has to be understood uniformly in a smooth truncation, say. Provided you have the A2, which we know are necessary, with tails, the two testing, which are necessary, weak boundedness, which is necessary, but it's going to disappear in a moment, and two other conditions that are so-called energy conditions, and we don't know if they are necessary or not. And I'm going to explain these two conditions in a moment. They are a little bit technical. Okay? I mean, a certain flavor of them. So in a sense, it's analogous to the NTV theorem. These take the place of pivotal, but these are weaker conditions than pivotal. If you have pivotal, you get this. Okay? And there is a certain approach to this theorem is to try to understand which are the weakest energy conditions you can get so as to try to prove they are necessary. So that's why there are, if you read our paper, there are like 4 or 5 different types of energy, because we're trying to see in which part of the proof is the weakest kind of energy you can consider. So let me define these energy conditions. It's a little bit technical, but anyway, let's go back to it. So first of all, there is a notion of a cube J being good. It depends on 2 parameters. This notion was introduced by Nazarov, Trail, Bolberg. So basically, you say, well, a cube J is good if you assume that either, oops, let me, here. So for every pairs of let's draw in one dimension. It's easier. For every pair of intervals, either j is very close to I in generations, very close is R generations, okay? Or if it is more than R generations away, this picture cannot occur. Meaning you cannot be too close to the boundary of I in a quantitative way, okay? And this is what's recorded here. That the distance from j to the boundary of k, well, k is supposed to be I here, is at least this quantity, okay? But this has to hold for every pair of intervals, okay? So then it's easy to check that the intervals you throw away, the j's like this that you throw away, is a small proportion, so you can simply forget about them. You can absorb them, okay? Good. So this is what we call, good. And this notion is R epsilon deeply embedded, what we call. And as I said, it depends on R. Well, this might be useful later, will be useful later. Then also, given a dyadic cube and a measure mu, you can, you look at the space of L2 functions with respect to this measure, which have integral 0. So this has dimension 2 to the n minus 1, and you have a certain Haar basis adapted to it, which in one dimension it has a very nice formula, and it's easy to write, and it has nice properties. In several dimensions, it's better not to write the formula. But the idea is that you have, on the one hand, orthogonality, and you have a certain telescoping property, which is typical of the martingales. Okay, so we define the so-called SubGood Haar projection, which is the following. For every interval k, you consider the maximal good subcubes of k, and then every guy below that, that is SubGood. And x is going to be the identity function. So then, whoops, the simplest flavor of the energy constant is this. So let me explain. You have an interval I. Well, this is going to be a soup over all dyadic grids, all dyadic cubes, all subpartitions. So the interval I, you partition into arbitrarily IRs. Any crazy partition you can think of. For each IR, you take the maximal R deeply embedded guys in IR. So these need not be good, because they are only R deep with respect to IR. So they satisfy this, but only with respect to IR, not with respect to all the guys above IR. And then you consider this expression, and you assume that, well, this is bounded on the corresponding dual. It's a mess, but okay. This is essentially the energy condition. It's a little bit more complicated, but this already captures enough of the flavor. One property, forget about these complications. It's simply, okay. One property of these R deep intervals, which is useful in some of the proofs, is that as soon as you are R deeply embedded, you are Whitney. Whitney means you dilate by 2 or by a certain factor, depending on R, and you don't overflow the interval, any interval that is R generations above or more. Okay. Good. So this was the theorem, as I already mentioned. Now I already mentioned this. So there is I mentioned that this was going to be removed. So this was an argument that Lacey and Wick found. They prove in half a page. It's a nice short argument, but very ingenious, using the NTV technique of surgery, that you can absorb the weak boundedness property from the other conditions. So basically, they show that weak boundedness is estimated by epsilon times the norm inequality plus A2 plus testing. So then you can absorb, and then it works. Okay, so you can remove that hypothesis. Good. So higher dimensional results. This is a short survey of the results, and then I'll explain a little bit more what's. The first one is the one I already mentioned, joint work with Eric and Chun-Jen. Then there is one instance which is sort of one-dimensional in a certain aspect that I will explain, which is joint work with Michael Lacey, Eric Sawyer, Chun-Jen Sen, and Brett Wick. So basically, you are assuming one of the measures is on a line. The other measure is arbitrary. Then the analog of the NTV conjecture holds. But again, one measure being on a line is, well, obviously one-dimensional character, no? And the geometry is complicated. So, it has to be a line, not even a smooth curve. It's really a line. for the proof to work. Or, I mean, okay, admittedly there is work in progress. We can do more than a line, but that's another thing I'm not ready to report yet. So, and then there is another theorem, which is just for fractional Riesz transforms, but codimension not equal to 1, in which you assume uniformly full dimensional measures. So this is something, whatever it is. Basically, it says that the measures are not, in a quantitative way, they are not concentrated on sets of codimension 1 uniformly over all locations and scales. Any doubling weight will satisfy this. Any R4 sub-irregular weight will satisfy this. Okay? Both in this Cauchy and in this case, even though the proofs are not formulated like that, but you can check it, in these two cases, you satisfy the energy condition here. So from a logical viewpoint, this is the strongest theorem right now. This is not in the chronology is a little bit more involved. But right now, as it stands, from a logical viewpoint, that's the, anyway, that's the strongest theorem. Although here, they did, I mean, I'm ignoring the common point masses issue here. Okay, but anyway, that's supposed to be basically just put holes in the A2 condition and run the proof. So the Cauchy one. The Cauchy one, you assume one of the measures supported on a line. The other one, well, let's say the open upper half plane, but you can immediately do the rest. You have Cauchy, and then you have the analog of the NTV conjecture. So basically, the norm inequality, or the norm, there's norm constant, is comparable to A2 and testing. Here, A2 and testing means whenever you test on the line, it's just regular intervals here. Whenever you test on the upper half, say upper half plane, you test on the Carlson cubes. But then otherwise the rest is the same. And it holds. Okay, good. I mentioned, yeah, reversal of energy. I need to explain a little bit what this is. In order to, for the one-dimensional case, there is one technical condition which is called energy reversal, which I'm going to explain in a moment. And this energy reversal is basically why we still don't have a higher dimensional analog of the Hilbert transform. Okay? It's a very special property of the Hilbert transform I will explain in a moment. So in these two cases, you can actually get, again, the proofs are not formulated like that, but you can read into them. And you can get energy reversal. As soon as you get energy reversal, you get the energy conditions. So what is this energy reversal thing? Let's go back to one dimension. We have an interval I, a measure supported far away from I. You do Hilbert against a Haar function supported on I. So morally, you should think of this as the derivative. Okay? And that's sort of the key. Where is this wonderful thing? Okay. That's sort of the key intuition. No? I just need to erase this part. Oh. Well, I don't know if I did a disaster, but anyway. So, as I drew before, when you have, so this is the interval I, your measure mu is supported here and here. You take h mu, so maybe I should, which is basically something like this. It's more or less like our tangent. The slope here is comparable to this. Okay? And that's sort of the main term in the Taylor expansion, and that's the dominant term. The inequality from left to right, appropriately modified. I mean, Brett and Michael got it, got the appropriate modification first. Holds in higher dimensions always, so that's fine. The reverse one fails miserably, okay? And that's the reason why we cannot push all the estimates to higher dimensions. No? So again, you might, okay. The simplest example was given by Michael. So assume you have the Cauchy integral on arc length of the unit circle. Then the gradient, again, if you think of this as the derivative, morally, then it's 0. So the gradient is the circle vanishes identically. There is no hope to get the left bigger than the right. But you might say, well, okay. I mean, Cauchy, after all, is very special, maybe with fractional Riesz transforms, because you immediate with codimension not equal to 1 to avoid Cauchy. After all, you have sign divergence. You have super subharmonicity. So then there could be a hope for left being bigger than right. in that case. And actually, that's sort of the approach in the lazy weak theorem. No, you cannot. I mean, if you assume their hypothesis in which you have energy reversal, fine. But in general, you cannot, and this is this theorem. So we can find a configuration for which the energy reversal, basically, as I said, is the left bigger than the right, fails for any vector of fractional smooth Calderon-Sigmund operators as soon as they have vanishing integral on every great circle in the sphere. Okay, a great circle means two-dimensional circle in this setting. So any odd Calderon-Sigmund operator fails. Berlin fails. I mean, and we can have such a configuration that fails for all of them simultaneously. So there was a previous example, well, or previous or essentially simultaneous, depending on example, but only just for Riest by lazy and weak. No? The proof of this estimate uses convexity of Fourier coefficients to give a positive density of measure, Bochner's theorem, which was a surprise, at least for me. I'll explain in a moment why. And, well, some computer algebra and third partial differences and residue calculus and partial fractions. So let me, well, I guess I have some time. So I'll give an idea of the proof of the failure of reversal of energy. So reversal of energy means that this is, which is basically the right-hand side, can be estimated by a certain uniform constant times, and this is essentially the left-hand side in the previous slides. No? And this is the so-called energy, which has, whatever expression it is. So when you try to build, I'm just giving some ingredients. When you try to get the general counterexample, it's sufficient to consider this kind of density in the circle. This will give you, as soon as this density is positive, you immediately get a counterexample. I'm skipping, obviously, some steps. No? So these BNs are certain coefficients which are complicated. So then it's sufficient, necessary and sufficient actually, that the following matrices are positive semi-definite. If you prove these are positive semi-definite, you immediately have a positive density. And I remember when I was in grad school, there is a similar condition, similar one, for Nevalina peak interpolation. And I was told, this condition is very nice, but it's perfectly useless. There is no way to verify it. And this is why this was a surprise, because with some work, we were able to verify it. So, well, it overflows, but it's symmetric. So, so then you can guess what the last column is. No? And we proved that the determinant of this is positive via certain recursion formula and some computer algebra and, well, partial fraction decomposition, residual calculus. So it works. So life is hard, I guess, because you cannot have this energy reversal. Now I wanted to go back. This is another part of some ideas of the proof of the big theorem. Okay? The big theorem meaning norm inequality. So the norm inequality if and only if, or hope of if and only if testing A2. In this case, also the energy conditions. But the scheme of the proof is there is essentially one scheme of proof, which is the one that was applied by Hilbert. But again, you need to. There are some complications. So you consider the dual. You consider the product. You dualize, and then you can decompose into pairs of intervals. So I and j, i's will correspond to this side of f, j to the g, and you have several cases. So this was the so-called, or what we call the NTV basic estimates. No? When the two intervals are disjoint, it's easy to handle. In the one-dimensional case, it was done by NTV. It works. You can estimate by NTV constants. NTV constants for us means testing plus A2. If they are if they are close in size, so R close or rho close, you can also estimate. That's fine. So then you are left with cases where you have a certain I and a certain j far below contained in it, or the corresponding dual. So this is I contained in j, this is the dual. It's treated the same way. So then this guy, you further decompose. So now you have to run two corona decompositions. The first one looks at how basically f and g, actually you only need to do it in f, how it behaves. So basically you stop every time you have the expectation over an interval sigma of I of f bigger than, let's say, 4 times the corresponding expectation, let's call it I prime. So you start with a certain interval, and each time you go 4 times above the previous expectation for the absolute value, you stop. Here is where I mentioned before, as soon as you have non-doubling, life is harder. This is one of the main reasons, because if we were doubling, we would have a control like this, if we were doubling. As soon as we are not doubling, you don't have control of how much you bump up by, and that creates complications. Okay? There is a second corona type decomposition for measures, which I'm not going to explain, it's more involved, but it basically says that a certain something close to the energy or pivotal sort of holds. No? So then once you are in the corona regions, basically, meaning that you have control both on the growth of the average of f and on the measures, then you can implement the NTV approach, in the sense that now you have good control and you are as if you had the pivotal condition. Okay? So then you can decompose. Okay. So let me explain here. This first rule gives you some stopping intervals, which I call curly f. So now you're considering pairs I and j. If you have some f here in between, so this I and j straddles the f, this is what we call the far term. Okay? So it's handled here, far below. So it's decomposed as well in several pieces, something that's called functional energy, which is like testing but for functions. And here, using the T of 1 type theorem for Poisson by Eric, you can handle it by NTV constants plus energy. So these 2 terms. So then you are left with some other term, which is when you're close. Namely, there is no such f in between. By the way, sorry, the f in between is what I called before the global part. The local part is when you have no f in between, so you're in the same corona. Okay? Now there's no f. Okay? This is what Michael told. So once you are in the local part, there is a certain nice trick, again, that as far as I'm aware, NTV did it first. I mean the first ones, which you have a paraproduct term, which is handled by testing, a neighbor term, which is handled by A2, and a stopping form. And it's a stopping form that you need to apply Lacey's recursive argument, appropriately modified for this context, and it works. Okay? So this is this is what I just explained. Okay. And then, in case we are not tired enough, I'll give you just a model estimate, which is one of the simplest cases, but it already has in its simplest form some of the ingredients we use. I already mentioned some of them along the talk. So I'm going to talk about this point here, this one. Okay? So where is it? Here. So we want to prove that once you have decomposed into the hard basis, basically, we want to say J is contained in 3i minus I, and it's sufficiently small with respect to I, and it's also good. Okay, and we want to decompose into. We want to estimate the sum by norm of f, norm of g, and one of the allowable constants, which is A2. As you can imagine, okay, in a sense, this is, in a different sense, it's similar to what, well, actually, Sasha's comment on sort of yesterday's talk by Terry Tao. No? It's, in a sense, everything is Cauchy-Schwarz. But you have to know where to apply it, and you have to know how to decompose the things into 25 million pieces so that you apply Cauchy-Schwarz in the appropriate place. So yes, everything is Cauchy-Schwarz, but not everything is Cauchy-Schwarz. No? Anyway, so one ingredient is that as. Can you remind us what good means? What? Sorry? Good. Yes, I'm going to remind you in the picture. I can give you the precise definition, but I'm going to remind you in the picture. Good means here is I. J is good if either you are very close, in this case with a parameter rho, or if you're far away, this cannot happen. Okay? There is the epsilon, blah, 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 but that's not, I mean, this is the picture. So because this cannot happen, you're Whitney. Namely, you're very small and you're not close to the boundary, so 10 times J is still contained in I. And this is what's reported here. Okay? Then, because you are Whitney, we can use the monotonicity lemma, which is this picture here. Because remember, you need to be somewhat far away from the interval where you're considering this. So we have what we call the pivotal bound. A pivotal, basically, because it's the bound that you would have if you could apply the pivotal condition, which is the simplest. I mean, this simply means, maybe I should explain. Well, this simply means that you are considering the projection onto the hard basis at level J. Okay, so all the 2 to the n minus 1 guys at level J. Okay? And this is the Poisson and the measure of J. So, yeah, now. The next ingredient in the proof of this estimate is that you pigeonhole the lengths of I and J. So the point is, we take the length of I to be 2 to the n, the length of J to be 2 to the n minus s. We expect geometric decay in S, and this often happens in this kind of arguments. We know that J is in 3i minus I, and we also pigeonhole the relative distance to call it 2 to the d. Because, I mean, this is the simplest case, so things now work beautifully, you know, and in a reasonably short way. So because of goodness of J, on the one hand, distance of I to J, because we're in the mid-range term, namely this, is at most 2 to the d. On the other hand, because we are good, we have this estimate. This is the precise definition, if you want, of, but it's, I mean, of the goodness, but anyway. So then you plug in the things, and you get a certain estimate for D, namely this. So D ranges in a very close, I mean, D moves in a very close range. So when you plug things into, into this left-hand side, I just copied the previous guy, but decomposing the sums into the different pieces. Okay? So the next step, in this case, we estimate the Poisson. In this case, we can do it brutally. Generally, we have to be much more delicate, much more careful. No? But in this case, J is 2 to the n minus s, and this is the worst case, 2 to the d. So we are just doing this. This we copy here. I mean, well, we're doing Cauchy-Schwarz in sigma, so that this is bounded by this. Okay? So again, the left-hand side is bounded by the same piece of sums. This 2 to the n minus s is here. This 2 to the d, sometimes whatever is here. The L2 norm is here. The sigma is here. This and this cancel each other, but we are preparing the A2 constant. And in the G term, which is here, which basically comes from here, we do Cauchy-Schwarz. I went too fast. We do Cauchy-Schwarz to get 3i and this guy. So this is basically, we are fixing the size of J. We are in 3i minus I, and the distance is like 2 to the d. So it's basically tiling 3i minus I, but by guys of this size. Okay, this is the A2 constant, so we can peel it off. The next thing is D only appears here, so we can sum the geometric series, and that's easy. Okay? So we get actually here A2 constant, which we peel off. We added up the geometric series, and now we do Cauchy-Schwarz simultaneously in I and N. We're using bounded overlap. This again appears often. I'll explain it in a moment. It's explained here. So you get some geometric series, decay in S, A2, and the two norms, so you win. What we often want for these kind of things to work is what we call diagonal estimate, namely the following. Assume F is decomposed into the projections onto the hard basis at size 2 to the n. And G is decomposed essentially the same size, maybe S steps below, but it's essentially diagonal once you fix the S. So then, if you have an estimate like this, you win, because you use Cauchy-Schwarz, and you win. And essentially, we always have to go back to this kind of diagonal thing. I mean, if you are doing sort of the square matrix brutally, we don't know how to do it. We always have to decompose so that in one way or another, we get into this diagonal type thing. And here, I mean, it's essentially diagonal because, well, we have bounded overlap, so it's the same. And thank you for your attention. Pardon me? Uh-huh. Actually, it's, well, I guess it's Herglotz, essentially. But it's contained in Bochner. Well, depends on how, okay. Okay. Yeah, actually, we can compute them, you're right. Classical system of? Okay. Yeah, okay. Good point, yeah, we didn't notice that. Thanks. Mm-hmm. We haven't, okay, so we have only looked at PP. Admittedly, as soon as you have two weights, you can consider PQ, why not? But in PP, we don't have a characterization. There is only a certain sufficient condition that it's pretty ugly. And we don't know, I mean, we don't have a characterization. And we have mostly, after we did that paper, we have mostly, it's in an, I mean, I can give you the reference later. It's Michael, Eric, Chunjan, and I in AP, analysis PD. Then, I mean, we focus mostly on the L2 case because it's supposed to be the easiest. And we still don't know how to get it. So yeah, but we don't. PQ we never looked at. And it makes perfect sense, of course. Yeah. Pardon me? Even in the other case? Yeah. Because, I mean, you lose orthogonality, you lose many of the tools that, I don't know. Mm-hmm. Yep. Yes. No, in the analysis of the local part, you just, I mean, there's a certain thing that Michael calls size, and you can do recursion. Actually, the analysis of the local to global. No, it's not needed. And the model, somehow the recursive proof of Michael somehow mimics also this guy of the far term, because he does a recursion from bottom to top, and he inserts some stopping cubes for that recursion. And then again, whenever you have a stopping cube in between that you're straddling for the pairs that you're considering, again you win. For a different reason, that the size gets smaller, but you win. And you're left with the other ones. And those ones you feed again into the recursion. But it's, I mean, there's a certain similitude in the global to local and in the handling of the local part. Yeah. Mm-hmm. By capacity, no. But as soon as one of the weights is doubling, you win. Even one, you win. No. By capacity, we didn't look at. You win meaning you get the characterization. You don't need both to be doubling. But yeah, we didn't look into capacities. Somehow, for operator theoretic reasons that I'm not so familiar with, but you actually want, I mean, the characterization being sought after is the comparability of the norm constant to A2 and testing.